example for rule 2 was this. If we have the residue, what example am I on? Forgot my numbers. 6, thank you. Residue of 1 over z cubed plus 1 times z squared at 0. Okay, so this is, look, so here's the story, guys. If you have something which is well behaved at 0, right, and that's just divided by z squared, that's a double pole. That's a double pole at 0. So rule 2 applies here. And rule 2 says I do what? I do the limit as z goes to 0 of d dz of what? Z squared times this, right? Do I need to write down how that goes? The z squareds cancel, and you just have what? See, so really what rule 2 is saying is that you do what? You rip off. Basically, rule 2 is saying this. If your function looks like g of z over z minus z naught to the power 2, right? Where g of z is holomorphic at z naught, then rule 2 says that the residue of f of z at z naught is simply equal to dg dz at z naught. There may be a case where the limit is needed, but oftentimes it's not. You can just differentiate and evaluate, all right? I'll put some quotes around here just to, I mean, the limit's there for a reason, I think, for mostly like the sine z over z issue and that kind of thing. If you were asking me to give you an example where the limit's needed, I probably can't do it at the top of my head at the moment. I'm sorry, but now I have to take this. So this is the other thing to think here is that, well, I mean, another way to look at this is just this. This is a fancy way of saying calculate this derivative and evaluate it at 0. That's another perspective on why we're taking a limit. It's really just evaluation, honestly. So this is differentiate what you got. You got yourself a minus 3z squared over z cubed plus 1 quantity squared, right? Because the derivative is a reciprocal function, minus 1 over the squared, different chain rule, 3z squared. I evaluate basically at z equal to 0. I'm just calling it like it is. Oh, man. Well, that's no fun. Is it 0? Lame. I don't like to be 0. Fine, it's 0. I guess that makes sense. Fine, it does make sense. I just don't like it to be 0. Phooey. Example 7. Here's one that's non-zero. If we had the residue of 1 over z squared minus a squared squared at a, that is the limit as z goes to a. All right, first of all, it's a double pole, see, because that's z minus a times z plus a, right? All squared. So in this case, my g of z, quote unquote, is really 1 over z plus a squared, if you want to keep with my lingo on this board up there. So I'm really looking at like d dz of 1 over z plus a quantity squared, which is going to give me minus 2 over z plus a quantity cubed. Evaluate that thing at z equals to a. And what we got? Minus 2 over 8a cubed minus 1 over 4a cubed, I suppose. There's the residue. Wait a minute. Oh, I just didn't simplify it in the notes. I'm a dummy. Any questions? Is this better than I mean, hey, an hour ago, before you knew about these rules, and the only way you could do it was to calculate the Laurent expansion, imagine yourself back in that place. Imagine where you are now. Love the rules. right? It's so much easier, my goodness. All right, so let me get the projector out here and show you rule 3 and 4. I actually tend to use rule 3 or 4 most. And there is a more general, oh man, what did I do that for? Stink. Did I ever tell you guys the joke about the rabbi and the let's see, I think this was a rabbi and a Russian scientist and a Polish janitor on a cargo plane. No, it wasn't a cargo plane. It was a commercial jet, and they were flying somewhere. Did I ever tell you this? No. I don't think I have. And so they were flying somewhere, and the co-pilot, he had just really bad food poisoning, and so he was incapacitated. He was, he had vertigo. He just couldn't even see to do anything. He couldn't fly the plane, right? And then the pilot, what happened to him? Well, shortly thereafter, 10 minutes after, the pilot had a massive heart attack, dropped over dead. There's just no one to fly the plane, and so the stewardess, flight attendant. What am I saying? What am I, a monster? Let's see here. Went over the intercom and said, well, we have no pilot. There's no one to fly the plane. Is there anyone here with technical expertise? And the rabbi said, no, I only care about spiritual things. I can't fly the plane. And then the Russian scientist said, I'm a theoretical Russian physicist. I can't fly a plane. That's experimentalist business, right? And then finally he said, well, how about you, sir, the janitor? And he said, but me, I'm just a simple pole in a complex plane. Yep. You are now part of the 0.2% of the general 0.02% of the population that can understand that joke. Worth the wait, right? No? That's part of why I want to teach this course. Like, this is the only course I can tell this joke in,
That should be the preface to your book.
Nothing has given me more joy than you correcting his pronunciation of Shikamaru, which I say incorrectly, but then again I don't have a tattoo.
It's a Chicago accent.
What do you guys think? Can a ninja throw a throwing star? Sure he can.
Yeah.
Oh.
That's right. There we go.
Get it? Sure. Japanese. Shuriken means ninja star in Japanese.
I'm just a math maker. You never played ninja games?
You never watched Ninja?
You never
Yeah, seriously. You never watched
one
Ninja?
No.
All right. Okay, so let me show you the remaining 2 rules. I probably should have made proof of these rules like homework problems, but I think I forgot to. Now, this here is something you should make sure you understand. This is kind of like the heart of the course is this theorem. All right, this is where the ultra instinct it flows from, this theorem. So if you have a function, right, with isolated singularities, z1 through zn, and if you have a contour which surrounds them, all right, so it encircles all the singularities, well, the integral of that function over that contour is simply equal to the 2 pi I weighted sum of the residues of the function. So we just have to calculate the residue of the function at each point, and we've got the integral. That is it's very nice. And the proof is really simple. I mean, it's just the Laurent expansion and the deformation theorem put together. See, because you can take this thing and you can put these crosscuts in, right? And you can encircle each singularity with a closed loop, which the function is holomorphic everywhere here except for the singularity. So you can just pinch it down and apply the theorem I wrote on the other board and calculate the integral around that loop as 2 pi I times the residue of z1. Likewise here, 2 pi I residue z2, and so forth and so on. But then the integral around all of the colored loops, right? When you add those together, all the crosscuts, they be canceling, and you're just left with the integral around the outside. And that is Cauchy's residue theorem. Which probably should, is it Cauchy's theorem or is it, Laurent? I don't know, whatever. It's Jeff's theorem. So here's rule 3. Rule 3 says if you have f and g holomorphic at z0, all right, and g has a simple 0, get this, g has a simple 0, then the residue of f of z over g of z is just f of z0 divided by the derivative of g at z0. That is super nice. Maybe next class, if I feel like it, I'll prove this, okay? But probably not, because it's going to be a video that I'm making for you guys, I guess. I mean, we'll have to have video class next time. I'm sorry. Unless you guys are like able to meet me sometime earlier in the day. But I think some people will be able to come maybe, but not everybody.
Say 6 a.m.
6 a.m., say not. I once upon a time agreed to a 7 a.m. topology with Dr. Skambordis. Never again.
With Dr.
Well, he was teaching, he was like the main teacher for topology at that point. Dr. Skambordis knows topology very deeply. And some days I would get here at 7 and he'd be like, oh yeah, I don't feel like topology today. Like, but I already woke up and I'm already here at 7. So, I love Dr. Skambordis, but I'm not signing up for one of them again. So, do I need to edit this? I might need to edit this now. Anyway, so this is f of z. This is g of z. Remember, we know that sine of z has a simple 0 because sine at 0. Because at pi rather, because sine of pi is 0, and cosine of, and the derivative of sine is cosine, and cosine of pi is -1. Therefore, it's a simple 0 by our simple 0 theorem. So sine of z is a simple 0 at pi, and so rule 3 applies. I do e to the pi divided by the derivative of sine, which is cosine at pi, and there you have it. That's the residue. That's nice. It's real nice. And here's another one. G of z's got a simple 0 at 3, voila, residue, calculated. And then finally, rule 4, if we have a reciprocal of a function with a simple 0, we just go back to rule 3 in the case f equals to 1. It's just 1 over the derivative. And so when you go back and you look at what we did with the partial fractions at the start, now in the, the cold mechanical light of rule 4, whoa, it becomes so much easier. Well, I don't know. Maybe there's not one in this. I guess not here. I think I've covered it up. It should be the next example in the notes. Anyway, let me just scroll down here a bit. So here's one. Check this out. Like, this has a simple 0 of I. Yep.
Sorry, I was wondering, does G have a simple 0 or simple pole at Z0?
It needs a simple 0. Yeah, my bad. That needs to be fixed. G should be simple 0. Yeah, thank you. I need to fix that. There's also something missing from the notes, right? Because I addressed simple pole and I addressed the double pole. What about the pole of order n? What's the rule for a pole of order n, right? I'll see if I can write that down in the video that I'm apparently going to make. And anyway, so here, simple 0 at I, and therefore the 2i. There's another way to look at this, though, you see. If we know that the partial fractions, right? If we know that partial fractions decomposition has weights, has coefficients which are given from residues, we can turn this around. We can calculate partial fractions by the rules. You can actually use the rules to set up partial fraction decompositions. And if we had the full the rule I'm talking about that's not in my notes, then we'd even be able to calculate the coefficients for repeated factor partial fraction decompositions by simply taking the rational function that you have, multiplying it by the appropriate power, differentiating it by the appropriate number of derivatives in evaluation. That would immediately give you the coefficient for that term in the partial fractions. So you could trade the partial fractions algebra for just a systematic bunch of differentiation evaluations if you wanted to. This could be very helpful in certain places. I've seen people use this. People who are really understanding it can calculate partial fractions very, very fast. And that brings us to integration. So now the next part of the story is to start using the residue theorem to actually calculate integrals. And we'll be able to calculate all kinds of improper integrals that we couldn't touch in calculus 2 by simply identifying them as part of a contour integral. And then the rest of the contour integral we're not interested in we'll limit to 0, but we won't care because we'll walk away with the integral from Calc 2 that we want.